Now let us discuss the last portion of 4th unit, Newton's formula for velocity of sound and Laplace's correction. We have completed these two topics. Newton's formula for velocity of sound. In our previous lecture, we obtained an expression for velocity of longitudinal wave traveling through gaseous medium or fluid enclosed in a pipe. So this relation means that velocity depends upon volume elasticity, that is bulk modulus of the medium and the density of the medium. So V equal to root over K by rho naught. So since sound is a longitudinal wave and Newton took advantage of this relation to obtain the velocity of sound in air. So we know that longitudinal waves travels in a medium in the form of compression and rarefactions. In this way we have already discussed. So compression, compression, then rarefaction, compression, rarefaction, like that. And from heat and thermodynamics, it is well known that when pressure increases in a gaseous system, temperature also increases. So during sound propagation, the compressed regions are at high pressure and hence at high temperature. Similarly, rarefied regions are at low pressure and at lower temperature. So Newton assumed that during sound propagation, heat can easily flow from compressed region to the rarefied region. That is, temperature remains constant. That is, equalize the temperature during the process, or the process is isothermal. So considering the process to be isothermal, that is T equal to constant, we obtain this relation for gas, PV equal to constant, and differentiating we obtain P dV plus V dP equal to 0, which in turn, after some mathematical rearrangement, we obtain pressure in terms of bulk modulus, that is pressure equal to bulk modulus K, which is equal to stress by volume strain. And so instead of here, actually in this expression of velocity of longitudinal wave, we can replace bulk modulus by pressure. So using pressure instead of bulk modulus, we obtain velocity of sound in air to be equal to V equal to root over P by rho. So this is the formula for velocity of sound in air. And if we now consider this case, the NTP case, at which pressure is this much and density of air is this much. So considering these two values in this formula, and if we calculate, then obtain V equal to 280 meter per second. That is, velocity of sound in air at NTP in accord with Newton's formula is equal to 280 meter per second. However, experimental value is 332 meter per second. So this is theoretical value, and experimentally measured value is 332 meter per second. So there is a difference between these experimental and theoretical values. So the discrepancy between these two values was corrected by Laplace. So in accord with Laplace, air is bad conductor of heat, and the compression and rarefaction occur so rapidly that there is no time to flow heat from one region to the other region. So that is what during the time of compression and rarefaction, through air heat cannot flow easily. So that is, the process is what? Adiabatic. And considering the sound propagation process to be adiabatic, that is, we in adiabatic case, for a gaseous system we have PV to the power gamma equal to constant, where gamma equal to Cp by Cv, the ratio between the specific heats at constant pressure and constant volume respectively. So we have this relation, and proceeding in the similar way, that is, the firstly differentiating this relation, we obtain P gamma V to the power gamma minus 1 dV plus V to the power gamma dP equal to 0, and using some mathematical simplification, after some mathematical simplification we obtain a relation finally, that is gamma P equal to K, that is bulk modulus in terms of gamma P. Initially in Newton's case, that is in isothermal case, K was equal to P. Now we have gamma times P, there is a factor. So replacing K here, we obtain velocity of sound to be root over gamma P by rho. This is the Laplace corrected expression for velocity of sound in air. So the value of gamma is 1.41 for air, and using the same values of pressure and density at NTP, if we calculate the velocity of sound, we obtain this value to be 333.6. that is, it is consistent to the experimental value. So this means what? Laplace's assumption is correct, and in this way we obtain a considerable value or way to have velocity of sound in air. Thank you.